Hello everyone, and welcome to Doing Math with Mickey. And let's talk today about the very first method of solving differential equations numerically. Now, at this point, you might be asking yourself, why do you want to solve differential equations numerically? You might be asking that, you might not be asking that, depending on your career or your experience with differential equations. But sometimes in real life, there are differential equations that describe the laws of nature that we really cannot solve analytically. Which is why we're going to talk about trying to solve them, not analytically, but try to approximate how the functions would look like if you try to just plug in numbers and see what happens. Now, the very first method was developed by Euler, the superstar of mathematics, physics, or in general just natural sciences. He developed the very first idea, again, of trying to solve differential equations numerically by looking at just the most simple differential equation that you can imagine, which is dy dx equals just some function of x and y. Now, why is that a simple differential equation? And why is that an important version of a differential equation? It is important because it essentially describes a field of slopes. We know that dy dx from very first calculus class that you might have been taking essentially means a derivative or change, instantaneous change, infinitesimal change, or slope. Well, these are just coordinates of that slope. And this is what we're going to be working on. Now, remember the formula of a slope line, y equals mx plus b, or in other words, just y1 minus y naught equal to mx1 minus x naught. Now, if you solve for y1, you get mx1 minus x naught plus y naught. The old y equals mx plus b. Now, from here, you can notice that m here stands for slope. x1 minus x naught essentially stands for change in x, and y naught and y1 are just the values of y. If I write this, I would get y1 equals to just slope, change in x, plus y naught. Now, this is the formula that Euler discovered, how to try to approximate next value of y by using the previous value of y. If I can rewrite this, I would say y1 would be equal to m, which is slope, which we already know is f of xy, the one that describes slope, delta x, and then y naught. Now, conventionally, delta x is denoted a little bit differently. So for this, as I was saying, in numerical methods, or at least in this class, the delta x will be denoted as just h, or a step. Essentially, what step you're taking in the x direction to find out the next value of y. So if I completely rewrite this to our final form with which we're going to be working with, our next value of y is dependent on our previous value of y plus h times f of x y, where f of x y is equal to the derivative of it with respect to x. Now, what are the common values for h for the step? It can usually it is expected for the step to be small compared to x at least, or to integers. So naturally, you would expect the h to be 0.1, 0.05, or 0.01. Within the vicinity of those numbers. Now, why not to start understanding this concept with an example? Example always helps. Now here we have an example of how we would apply the Euler's numerical method to try to approximate the numerical value of the function. Now, we have the y prime or dy dx equal to the function of y minus x. We have our initial condition that y at x equals 0 equals to -1. We have our step function, which is 0.1, and we have our question, which is what will the numerical method give us for y equals 0. The value of y at x equals 0.5. Now, if you look at the slope field that has been produced by Mathematica and marked with a red dot, where our initial condition is. Our initial condition, again, is that x equals 0, our function y equals to -1. How will we try to approximate the numerical value of our function graphically? We would, again, just mark our initial condition on the slope field, graph the slope field, and then try to use a slope line as slope formula for a line. How we do this we'll look at the initial condition, we would see what slope it is, and graph our line for our step. Then we would have our new point. Then when we take that point, we would look at what slope it is at that point, and we would draw another line. And so on and so forth until we reach to our x equal 0.5. And so on and so forth. Let's try using our formula. So we have our y1 that equals to our step times the function of the slope plus the previous value of y. We know our initial value of y to be -1. We know our initial value for x to be 0. And let's apply the formula. y1 equal to our step, which we know is 0.1, times our slope function, which is y, -1, minus 0, minus 1. Now, if we do the algebra, do the calculations, we should get that our y1 should be equal to -1.1. I also like to use a table, not to get confused with my values of x and y. I would just do a simple table, x, y. Let me redraw this to this. And I know that at 0 was -1, and I know that at x, negative x, at the negative x, we would have the value of -1.1. How will we find the next value of x? Remember how we discussed that the h is the delta x? I could also say that my x1, the next value of x, is simply my previous value of x plus the step. So if we apply this, we get that our next value of x is just 0 plus 0.1, which is just 0.1. So we know that for x to be equal to 0.1, our function of y equals to -1.1. Now, let's continue. Let's find our function of y at x equals 0.2. What do? We take our previous values of y, plug it into the formula, see what happens. So we do our y of 2 equal to the same step times our new values, x1, y1, plus y1. So our y2 is 0.1 times, what was our new x? what was our formula? Y minus x. So we take our previous values of y, negative 1.1, and minus 0.1. Minus 0.1. What do we get? If we put it in a calculator, we get that our next value of y is negative 1.22. Negative 1.22. Now, if we do the same for y3, we get that we use our, again, previous values of y that we just calculated, h times f of x to y2 plus y2, which is just 0.1 times negative 1.22 minus 0.2 plus minus 1.22, which is, if I plug it in the calculator, I get negative 1.362. If I put it in the table, it would be negative 1.362. Now we're 2 steps away to calculating our value of y at x equal 0.5. Let's continue. So if I continue doing this, I continue doing the same thing. I just plug in our previous values of x and y to find our new values of y. So it would be still 0.1 times negative 1.362 minus 0.3 minus 1.362, and we get for it to be equal negative 1.5282. 5282. If I do this one more time, I get this negative 1.5282 minus 0.4 minus 1.5282. And we get our value to be negative 1.7210, approximately. And here we go. 7212. We just used Euler's formula to approximate what a function of y might be equal at x equals 0.5. So that would be your conclusion about this problem. Now, with all due respect, Euler was the very first person to try to discover the numerical approach to solving differential equations. However, since it was being the very first method, it is very much full of error and deviations. Because you're just using the very first derivative, you're not approximating the function too well. And then you might see that if you look at my other video of how to do Euler method in Excel. There I show how to graph the Euler method in Excel by using Excel. Very fast, very easy, while also comparing it to the actual solutions of y. And you can see there that with more and more steps you take to approximate bigger and bigger values or further away from the initial condition, the more error you will accumulate. Now wait, there's going to be also a second part to this video to be continued, which will discuss another numerical method that you're going to be using and studying called RK4 method, which you will see is much more efficient and has much less errors than the Euler's method. Now, this was the video of the procedure of how you would go with solving a differential equation numerically using Euler's method, and that's it. Thank you for listening.